Alright, so in this video, we are talking about objective 5.5, multi-step trig equations. With unlike terms, we are solving them with Pythagorean identities. Of course, these are the Pythagorean identities. You should have them memorized because of studying objective 5.3. We are going to specifically be looking at problem type E, which is the Pythagorean identity problems. So in these problems, we have quadratics. It almost looks like maybe we could factor them or use the quadratic formula, except we have unlike terms. So the idea behind this is we want to use our Pythagorean identities to replace the squared terms with like terms. So I want to replace this tangent with something in terms of secant. I want to replace this sine with something in terms of cosine, and I want to replace this sine in terms of something in place of cosine. We could do the same thing for cotangent and cosecant. Of course, we just didn't have any examples for this particular video. I am not going to solve them all the way. This video will only focus on the substitution. So if you're having trouble with factoring or the quadratic formula, I recommend that you go back and look at videos over type C or type D. Those were both 5.4 objectives. So this is only dealing with the substitution. So let's look at number 1, tangent squared theta plus secant theta equals 1. Now, as always, we need to be equal to 0. So plus secant theta minus 1 equals 0. And now I need to turn this tangent into a secant. So we're going to look back up here at identities. Our identities, only one of them has tangent and secant. That's this third one. So I'm going to do this in red, so you know I'm actually only looking at the identity right now. I don't care about this problem for the moment. I'm going to say tangent squared theta plus 1 equals secant squared theta. That's our identity. And I'm going to solve it for tangent squared theta so I can figure out what I can replace this with. So that just means I subtract 1, and I get tangent squared theta equals secant squared theta minus 1. And now I can take this and replace it with this. So that is secant squared theta minus 1 plus secant theta minus 1 equals 0. If there was anything to distribute, I would, but there's just a 1 out here, and we don't even have to write that. So that becomes secant squared theta minus 1 plus secant theta minus 2 equals 0. We can combine our like terms, so negative 1 and negative 2. I don't know where that negative 2 came from. That should be a negative 1 as well. Sorry, I rewrote that wrong. Secant squared theta plus secant theta, negative 1 minus 1. I was getting ahead of myself. Now it's minus 2 equals 0. And now we will solve by factoring or the quadratic formula. So you can go back and look at videos for type C problems or type D problems, and that will tell you how to finish this type of problem if you are still having trouble. Let's look at another substitution example. 1 plus cosine theta equals 2 sine squared theta. Well, I've got a square right here. That tells me I want to use a Pythagorean identity. I want to turn sine into cosine. And we only know one identity that deals with sine squared and cosine. It's the first Pythagorean identity we learned. Sine squared theta plus cosine squared theta equals 1. So let's figure out what is sine squared theta. So we're going to solve for that. And we do that just by subtracting the cosine squared away. So sine squared theta equals 1 minus cosine squared theta. And we will substitute that for that. Of course, I didn't set this equal to 0 first thing. We can do that at the end, and it'll be okay as long as we do it before we factor. 2 times 1 minus cosine squared theta. And now we only have cosines. And we can reduce this. I will distribute the 2. 2 times 1 is 2. 2 times negative cosine squared is negative 2 cosine squared theta. Let's get it set equal to 0. So add the 2 cosine squared theta to both sides. So I get 2 cosine squared theta plus cosine theta plus 1 equals positive 2. This 2 is still down here. Subtract the 2 from both sides. 2 cosine squared theta plus cosine theta minus 1 equals 0. And now we can factor or use the quadratic formula to solve. Once again, videos over type C and type D will help you learn how to do those two methods. And one more example. Very similar to the last one, but let's just make sure we really get what we're doing. This was a little more straightforward. Still sine squared theta, and I should already know, if I've done the last problem, that sine squared theta is equal to 1 minus cosine squared theta. So the nice thing about doing a lot of these problems in a row is you're going to be able to use the same identity multiple times. So I don't have to sit there and solve the identity every time. If you go back and look at problem number 2, I already know that sine squared theta equals 1 minus cosine squared theta. So I can save myself some time, and you might even memorize some of these eventually if you do enough of them. I just replace the sine squared with 1 minus cosine squared. Minus cosine theta plus 4 equals 0. We will distribute. 2 times 1 is 2. 2 times negative cosine squared is negative 2 cosine squared. Minus cosine theta plus 4 equals 0. We have like terms of 4 and 2, so that is negative 2 cosine squared theta minus cosine theta plus 6 equals 0. And I just want to point out one thing at this point. From here, I would need to factor or use the quadratic formula, as I've been saying. I don't like for my leading term to be negative. So I don't know if I've talked about this in any of the other videos yet, but if I want this to be positive, I'm allowed to do that as long as I change all the signs. And when I say all of the signs, I mean first, second, third, and the one on the other side. Of course, negative 0 is still 0. But this can be rewritten as 2 cosine squared theta plus cosine theta minus 6 equals negative 0, which is just 0. You don't actually even need this sign at all. So that's just a little tip. If that makes it easier to factor or use the quadratic formula, I recommend trying it out.